So hey guys, this is Dipesh, and in this particular video we'll be talking about recurrent neural network. So we'll see what recurrent neural networks is, how it works, and in the second part of this video we'll try to implement recurrent neural network using Keras library. So yeah, let's get started. So recurrent neural network is basically mainly used for sequential data, okay? And natural language processing is basically a field where we mostly deal with sequential data, okay? So recurrent neural networks has been specifically made to deal with sequential data, okay? So keep that thing in mind. So before we jump directly into recurrent neural network, let's learn some things about natural language and also some other methodologies in natural language processing, okay? So first of all, what exactly is a natural language? Now in natural language is kind of an opposite of a programming language, okay? So in computer programming we have various programming languages like C, Java, C++, etc. But the main difference is that these kinds of languages are human created. We as humans have developed these languages in order to operate our computers, but a natural language is not something that has been invented. It has been developed and evolved naturally over the centuries, okay? So English, Hindi, French, all these languages are, we can call them as natural languages that we as humans use every day in our lives, okay? Now the field that deals with natural language is called as natural language processing, or NLP, okay? Natural language processing, or NLP, which is basically automatic, which deals with basically processes and analysis of natural language, okay? So for example, in from a deep learning point of view, from a deep learning point of view, in natural language processing we basically deal with natural languages. So anything from language translation to text recognition to text summarization, anything that deals with natural language, okay, or textual data basically, we can basically, that comes under the NLP field, okay? And in deep learning we create NLP models using recurrent neural networks, okay? And these are basically some of the problems that we can solve using recurrent neural networks in the field of natural language processing. So we can do language translation, that is translate one natural language to another language completely. Then we can do sentiment analysis. So what sentiment analysis means is you give the model a sentence, and the model will basically predict if the sentence is positive, negative, or neutral, you know. Then there is text summarization. So text summarization is basically one of my favorite applications. So what you do is you just give a big chunk of text to the model, and the model will basically summarize this entire chunk of text in just few lines of code, in just few lines, okay? So it can be you can give for example, you can give the model a newsletter, okay? And the model will basically summarize the entire newsletter into few lines. So these are basically some of the applications that we can do in using deep learning, okay? So again, natural language processing is basically a field that deals with natural languages, okay? And from a deep learning perspective, using recurrent neural network, we can create various NLP models to solve various NLP problems. So that may include language translation, text summarization, sentiment analysis, all this, okay? So now, how do now since the textual data that we are dealing with, it is in a string format, and we know that our deep learning models cannot handle textual data. Basically they cannot handle string data. They can only handle numerical data. So one of the major subfields of natural language processing is text processing, okay? So text processing methods basically include how do we convert this string data into into numerical data. So basically, how do we convert text into into numbers? Okay, that is, how do we convert words into numbers such that we can easily give a sentence to our model. Okay, so in natural language processing, we mainly deal with textual data. Okay, so it is very important to know the methods to convert text into numerical format. Okay, now some of the very common methods that are used to do text processing, that is to convert text data into numerical format, are one-hot encoding, bag of words, and word embedding. Okay, again, some of the most common methods to convert text into numbers is are one-hot encoding, bag of words, and word embedding. Okay, but unfortunately, basically each of them requires their own separate video, because unlike other deep learning models like multi-layer perceptron or convolutional neural network, recurrent neural networks basically need a lot of pre-processing. Okay, even though recurrent neural networks are very easy, okay, in terms of their architecture, the the pre-processing, okay, the pre-processing that is needed in order to train a model is very huge. Because let's say you want to do language translation, okay, then you have to basically collect all the different sentences, then from all this and also collect their answers. That is, let's say you have English and you want to convert English into French using a language translation model. Now what you have to do, you have to basically first collect various, like millions of sentences in English, and also their translation in French. Okay, and then what you have to do is, for both these for all these sentences, you have to basically convert each and every word into a set of numbers. Okay, basically you have to convert each and every word into a vector. So this is basically a very time consuming task. So that's why it is very important that you at least know some basic things how to about converting text into numbers. Okay, don't worry about recurrent neural network, it's very easy. In terms of natural language processing, I would recommend that you spend more time learning about these various methods. Okay, now these three are not the only methods, there are also a lot of other methods. Okay, but it will but it will but each method will basically take its own video. Okay, so that's why we won't cover all these methods. What we'll do is we'll cover one hot encoding, which we have already seen in our previous videos. Okay, we'll see how we can convert text or numbers into vectors using one hot encoding. All right. Okay, now also remember that usually usually basically our aim is to convert words with similar meaning to have similar values. Okay, so for example, we have two words, let's say dog and dogs. Now dog and dogs are very similar to each other. Okay, both basically means basically some kind both words dog and dogs deal with only have only one meaning. Okay, because both these words mean dog. So there is kind of a similarity between their meanings. So what our aim is to basically our aim with basically these natural language processing methods is that to convert to give vectors or to give numerical values to words with similar meaning to have similar values. So you can see that dog and dogs kind of have similar values in their vector. Okay, they both have 11, then they both have 3, and their values are pretty close to each other. Okay, so if you plot these values, okay, if you plot this kind of vectors on a 2D Cartesian coordinate system, you will see that similar values, similar words are very close to each other. So this is our goal here in natural language processing, that whenever we are trying to convert text into numbers or words into vectors, our main goal is to basically convert words that have similar meaning to have very close values. Okay, so again you can see that there is father and boy. Okay, now father and boy are not very different from each other. Okay, they are not very far from each other. So so if you look at their vectors, their values will be very close to each other. Okay, then then there is again fast and then there is slow and slower. Okay, now slow and slower are again kind of very similar to each other. Okay, so that's why basically uh, we basically aim to have their vectors to have similar values. Okay, but what we'll do is in this video I won't tell you we won't discuss methods that do this thing. Okay, we'll discuss one hot encoding. Okay, one hot encoding is very easy, but one disadvantage of one using one hot encoding is that we cannot do something like this. Okay, we cannot create have words that have similar meanings to have similar vector values. Okay, but usually our goal is basically this. So now let's see how we can convert words to vectors using one-hot encoding. So it is one of the simplest methods to convert words to vectors. We essentially represent each word as a vector of length v, where v is total number of unique words available in the entire textual data. Okay, v is also called as vocabulary count. So for example, if you take this, okay, if you take this sentence, okay, just let's assume that this is our entire text data. Okay, now in reality we have when we are talking about natural language processing data sets, they may contain millions of sentences. Okay, so just to keep the matter simple, okay, and to understand things very clearly, just assume that this is our entire data set. Okay, these two sentences, that is deep learning is hard and deep learning is fun, this is our entire data set. So then what we'll do is we will aim to convert each unique word in this sentence to have a numerical value or to have a vector value. Okay, so since so first of all what we will do is we will count how many unique words do we have. So in this entire data set, we have, let's say, we have 3 to 4 unique words. So deep is one, learning is one, is one, then hard is one, and then fun is one. So we have in total 5 unique values. So our v is equal to 5. So then now what will happen is basically we'll we'll try to handle each we'll handle each unique word as a separate categorical class. Okay, just like we do in one-hot encoding. Okay, in one-hot encoding, when we apply one-hot encoding to a categorical variable, we basically assign a new we basically assign a single value to every single class. Okay, so in the similar fashion, we'll uh, we'll assign a single value, a single digit value to each unique word. So since we have 5 unique words, what we'll do is we'll create a vector. Okay, we'll create a vector with 5 values. Okay, 5 digit values, and wherever the vector that represents any one particular word will basically have either 1 or 0 in its place. So again, let's discuss this again. What we are doing is we are trying to convert our textual data into numerical format using one-hot encoding. Okay, and what we just did is we this is our entire data set. Okay, and we are trying to convert this entire data set into or this entire or this or the words in this data set into vector format. Okay, so since our entire data set consists of 5 unique words, we will have a vector with five values. So for example, if I want to represent, let's say, deep, okay, if I want to represent this word in one hot encoding format, then what I will do is I will write 1 at first position. I will write 1 at I will write 1 at first position. Okay, let me just okay, so we have 1 at first position, and then what we'll do is we'll uh, we'll basically assign 0 to all the other values. Okay, we'll basically assign 0 to other values. So we now have three values remaining. Okay, so now this vector, if you look at its length, it has five digits. Okay, five different numerical values. Now this vector basically represents the word deep. Okay, it represents the word deep. Now let's do it for learning. Okay, let's do it for this learning word. Now what we'll do is we'll just copy this vector. Okay, we'll just copy this vector. Okay, now what we'll do is we know that the first value basically represents deep word. Okay, this word deep word, that's why it has 1 on its first position. But the second position, the learning. Okay, now the learning basically we want to represent the learning word. So what we'll do is we'll put 1 at second position, and we'll do 0 at first position. Now this vector, okay, this vector will basically now represent the learning word. Okay, so we'll do the same thing for all the unique words. Okay, we'll do the same thing for all the unique words. So basically what we are doing is we are treating each unique word as a categorical class. Okay, so yeah, this is how we convert our textual data or our words into vectors. Okay, so let's summarize this again. Okay, so let's go step by step. So the first step would be so this is our data set. Okay, this is our data set. Data set is basically deep learning is hard and deep learning is fun. So we have 5 unique words in our data set. So the first step what we'll do is we'll remove all special characters from the data set. Okay, so if you look here, let me clear this. The first step that we'll take is we'll remove all special characters and punctuations. Okay, so if you look at our data set consists of a exclamation and some commas. Okay, so in the real world, so when you will be making models, we only want to deal with words, we don't want to deal with punctuations. Okay, so that's why what we'll do is we'll remove all the special characters. Now this is our data set after removing all the special characters. Okay, now the second step would be we have to count the number of unique words in our data set. That is, we have to find our vocabulary count. So we know that in our data set we have 5 unique words, so our V would be 5. Okay, our vocabulary count would be 5. Now what we'll do is we will basically apply one hot encoding on each unique word of the data set. Okay, so since we have 5 unique words, this is how each vector will look. Okay, you can see that deep basically is represented by this vector, then learning is represented by again this vector, Okay, also since we have five unique values, our vector length is 5. Okay, the length of our vector is also 5. So keep this in mind. So this is how basically we convert uh, uh, words into vectors, okay, or into numerical format. All right. So let's also discuss some of the disadvantages of one-hot encoding. So the size of the words, okay. Now the size of these words, one mega main disadvantage is the vocabulary length. Okay. Now in one-hot encoding, what we do is we count the total number of unique words, okay, and the length of our vector, the length of our one hot encoded vector is equal to that equal to our vocabulary count. But this is basically a very simple data set. Okay, this is not, we can't even call this a data set. Okay, we just have two sentences with five unique words, but in real life we'll have, when we have millions of lines of textual data, in that situation we may have hundreds of thousands of unique words. Okay, so basically if we have hundreds of thousands of unique words, then our one hot vector, okay, one hot vector will also contain thousands of numbers. Okay, and in order to basically represent just one small word, we would have to basically use this vector with thousands of numbers. So it's also a lot of waste of memory and time, because you can observe that it's not efficient to basically create this one big vector and place just one at any one particular place, just to represent one unique number. Let me repeat this again. uh, One disadvantage of one hot encoding is that the size of each word's one hot encoded vector is always equal to v, which is the size of the entire vocabulary. In the example it was just 5. Okay, but usually the value of v, that is the value of vocabulary, can reach to 5 used to 10,000 k. Okay, or even 100k. So in real life the vocabulary of humans is very huge. We usually have thousands of unique words in our entire vocabulary. Okay, so we would need a very big vector, a very huge vector, just to represent a single word. Okay, which is basically a waste of memory and time. So that's why it is we usually don't use one hot encoding if our vocabulary, or if we have very large amount of textual data. Okay, the second disadvantage is that it does not hold any semantic meaning. It does not hold any semantic meaning. So just as I said in earlier, what our goal is when we are trying to convert words into vectors, is that we want to convert words that have similar meaning to have similar vector values. Okay, but in one hot encoding we cannot do something like that. Okay, if I just give you this one single vector. Okay, now this vector, basically I can tell that this vector represents the word hard, but I cannot tell that where the hard where the word hard comes in. Okay, I cannot tell you where the word hard is placed, right? So it does not hold any semantic meaning. Okay, for again, if I give you just the word learning, okay, you can tell me the numerical format of the word learning, but you cannot, but it won't be possible for you to locate where the word learning is situated in this entire data set, right? So this is also one of the main disadvantage of using one hot encoding. So yeah, that was it for one hot encoding. Now what we'll do is we'll jump straight into recurrent neural networks. So just let me have a sip of water and then we'll continue. Okay, so recurrent neural networks. So recurrent neural networks are a special type of neural networks designed to handle sequential data. Okay, now sequential data means basically mostly textual data. Okay, so RNNs are designed specifically for the task where the sequence of the input matters. Okay, that is the output of the model depends highly on the sequence of the input. So RNNs kind of have a memory which captures information about what has been calculated so far and provides the context to the network. Okay, the word context is very important. So basically, whenever you have certain problems where the sequence of the input, okay, sequence of the input matters, that is the output of the model highly depends upon the sequence of the input data. In that case, we use recurrent neural network. Okay, and recurrent neural networks kind of have a memory. Okay, they have something, a memory feature, which kind of helps us, kind of provides context to the neural network. So one example would be language translation. So let's say we want to convert English to French. Okay, and if I give the sentence where is hospital to the model, then the model will basically create a certain type of input. Okay, the model will basically convert a certain provide a certain output. Okay, so if I give where is hospital, then the model will also give me where is hospital in French. Okay, but if I don't maintain the sequence, okay, if I jumble this sentence somehow, okay, and if I gave this jumbled sentence to a model, now the sequence of the input is changed, so the model will also change the output that it's giving me. Okay, so here you can see that the sequence of our input matters a lot, right? The sequence of our input basically determines the what output we get. Okay, so another example would be text prediction. If I just gave let's say we want to give a sentence as input, we want the model to predict the next word. Okay, so if I gave where is the, okay, if I just give where is the, then the model will basically predict it as hospital. But if I give something else, okay, if I jumble this sentence, okay, is the where, then the model may give some other output. So again here you can see that depending upon the sequence of the input, okay, here you can see that both the inputs that we gave contain same values, okay, same words, but the sequence has been changed. So this is what you call as sequential data, and RNN are basically designed to handle this kinds of problem where the sequence of the data matters. Okay, sequence of the input matters. So also let's look into different architectures of RNN. Now RNN, okay, recurrent neural networks are very different from our multi-layer perceptrons. Okay, so don't think of our recurrent neural networks as something simple like a multi-layer perceptron. Okay, so in most of the models that we saw here, they have the input that we gave to the models was predefined. Okay, predefined sizes. So for example, if this is our model, okay, let's say this is our CNN model and this is our ANN model, then we had a predefined size of inputs here. We had a predefined size of inputs here. For ANN, we basically had a predefined number of independent variables. You know, if we had three independent variables in our data set, then our main goal will also be to basically have three input nodes in our input layer. Okay, so there we have a fixed size of input and a fixed size of output. Okay, we have predetermined input size and predetermined output size. Even in CNN, we basically have the size of the images that we give to CNN is predefined. So if I have, let's say, a 10 by 10 image, okay, 10 by 10 image, then all our images will also be of the same size, okay. And a CNN will also have a fixed output, okay. If a CNN has only one, if a CNN has one node in its output layer, okay, in its output fully connected layer, then for all the samples the output will remain the same. So in both the cases, the input of the model and the output of the model have a fixed determined size. But in case of RNN, we don't have that kind of thing, because let's say you have a language translation model. Now you can either give a sentence of 5 words, or you can also give the model a sentence of 10 words. So the size of the input, size of the sentences is varying. Okay, so we cannot have a fixed length or fixed size of our input. And also, depending upon the size of the input, the output also changes. Okay, depending upon the size of the input, the length of the output also changes. So this is one major difference between RNN and the other models. All right. So yeah, let's look more into it. So one issue with vanilla neural networks and CNN is that they only work with predetermined sizes. They take fixed size input and produce fixed size output. RNNs do not actually have this constraint. Instead, their inputs and outputs can vary in length for different use cases. Okay, so depending upon the use case, the input and the output, the length of the input and the output basically changes. So if you look here, so these are basically some of the common architectures of RNN. Okay, so some of the common architectures are one to one, one to many, many to one, and many to many. So in one to one problems, RNN basically takes only one input, okay, that is one word, and it produces another word as input as output. In one to many, it takes one input, okay, it may take basically one word, and it may produce multiple outputs. Okay, what you are seeing right now, this is basically a common this is basically a common architecture of RNN. Don't think of them as similar to multi-layer perceptron. Okay, they are quite different from multi-layer perceptron. But just remember that since the input length and the output length can change in recurrent neural network according to the input, we don't have any predefined structure to this to the architecture of RNN. Okay, so depending upon the input and the output, we have multiple types of architectures. So we may have one to one, wherein we have only one output and one input, or we may have one to many, uh, where we have one input and we want multiple outputs. Then we have many to one, where we take multiple inputs and we have only one output. Okay, then we have many to many. So many to many is the most commonly used architecture, wherein we take multiple inputs and we produce multiple outputs. This architecture also called as sequential models. Okay, sequential models, because we are inputting our input is also a sequence and our output is also a sequence. Okay, so don't focus on them. Okay, as a beginner, don't focus on them, just focus on this. Just basically, these are not different types of recurrent neural network. Okay, this is basically same recurrent neural network, but with different architecture depending upon the problem that we are trying to solve. So for example, let me give you examples depending upon these various architecture. So for a one-to-one architecture of RNN, a good example would be predicting the next word. So for a one-to-one architecture basically represents one input and one output. So this can be used in cases like when we want to input the model, give a model one word, and we want the model to predict the next word. Okay, so here we have one-to-one mapping here. That's why we call this architecture one-to-one. Another example would be for one input to many outputs. Now, one example for this would be image captioning. Okay, so image captioning, basically in image captioning, we have an image. Okay, we give this image to our model, and the model basically uh, outputs a sentence, okay, or a caption for this image. So here the image is basically one input, and we are getting multiple sentences out from our RNN. So there is one to many relationship here. Okay, so there is one to many relationship. Now let's take an example. Look into an example of many to one model. Okay, many to one, basically it can be used for examples like sentiment analysis. Okay, so where you give a sentence as input, and you want one particular one thing as output. That is the state. That is an emotion. Okay, let me show you an example. So here, so we give in sentiment analysis, we give a sentence to our model, and you try to, and we expect the model to basically predict the sentiment here. Okay, it's so the sentiment can be either positive, negative, or neutral. So this is basically an example of many to one relationship. So we are sending multiple words to the model, okay, and we are getting one output. Now another architecture is many to one. Okay, so a very good example for many to one architecture is language translation. So you saw here that we can give multiple words. Okay, we can give multiple words to the model. Okay, well, now when I say multiple, when I say many to one, it basically when I say many to one, or one to many. So many here, the word many, okay, the word many represents multiple words. Okay, so basically, since we are dealing with textual data, when I say many or multiple inputs, it means saying multiple words. I'm meaning multiple words as input. So here, in a many to many language, in a many to many RNN architecture, we give multiple words to the model, and the model again outputs multiple words as the output. Okay, so this is one example for many to many architecture is language translation. Okay, so don't worry about this. Even if you don't understand this, this is basically just for your own understanding, just to improve your understanding of RNN. Okay, we in reality we may not have this kind of distinction between RNN models. Okay, but just keep these things in your mind. It is very important. It makes learning recurrent neural networks very easy. Also, you can easily derive your problem, easily, basically depending upon your problem, you can easily decide which architecture to use. So if you want to, let's say, take any sentence, and you want to predict some another sentence, then in that case you can easily distinguish here that this is a many to many relationship. Okay, that's why we can use a RNN architecture with many inputs and many outputs. Okay, so just like this, just keep these things in under your in back of your mind. So now let's look into recurrent neural networks and how they actually work. So as I told you earlier, recurrent neural networks are basically a special class of neural networks which are designed to deal with sequential data. Okay, which are designed to deal with sequential data. So uh, that's why the sequence of the input basically matters here. So in other neural networks, all the inputs are independent of each other, but in RNN, all the inputs are related to each other. Okay, so RNN basically remembers all the relationship while training itself. Okay, so as I told you earlier, there is basically a kind of relationship between the inputs. Okay, so depending upon the sequence, we get an output. So sequence here matters. Okay, sequence basically means context. So now, in order to achieve this, what RNN does is, an RNN basically creates a loop with itself. Okay, an RNN basically creates a loop with itself. Basically, this loop allows RNN to maintain information. Okay, now again, this is how our recurrent neural network looks like. Okay, this is a recurrent neural network. Okay, this is not a recurrent neural network. Okay, I will explain this part to you, but just remember that this entirely the entire architecture of a recurrent neural network is just like this. It's just this one loop. Okay, the architecture of a recurrent neural network is not very complicated. Okay, it's very easy. So again, a recurrent neural network is not a fully connected layer. It is just folded over time in order to take an input sequence of undefined length and also maintain information about previous words. RNN creates a loop with itself. Okay, so what RNN does is, you can see here, RNN is creating a loop with itself. Now, what this loop does is, it helps RNN basically maintain information or maintain context. Now, the reason why we have this loop is because is to basically persist context, or to persist previous inputs. Okay, to persist information of previous inputs. The way RNN does is basically by something called as a hidden state. Okay, by something called as hidden state. So hidden state is nothing but it is a simple vector. Okay, hidden state is nothing but a simple vector which is basically looped, which is basically passed as input again and again to the RNN cell. Okay, this is the RNN cell. Okay, this is called as a recurrent cell. So a hidden vector is not a hidden state, basically helps RNN maintain information. Okay, it helps recurrent neural network maintain its context. So a hidden state is nothing but a simple vector. So it can be of any value. It can be of any length, or it can contain any values, any numerical values. Okay, just keep this in. Just remember that hidden state is nothing but a vector, and this vector basically helps recurrent neural network maintain or persist context. Okay, to maintain data, to maintain the relationship between the inputs. Okay, to maintain this sequential relationship between the inputs. Now this hidden state is basically given as input to the recurrent cell multiple times. Okay, through the loop, through this looping mechanism, where it is given as input to the recurrent cell multiple times. So what you are seeing here, okay, what you are seeing here is not a fully connected layer. It's not a multi-layer perceptron, but rather it is a single recurrent neural network. Okay, this this part is all the this is the entire architecture of the recurrent neural network, and this is the unfolded version of the recurrent neural network. This is basically done just for our own understanding. Okay, in reality, the architecture of recurrent neural network is not like that, like this. The architecture of recurrent neural network is this. Okay, it has one recurrent cell. Now this recurrent cell basically takes two things as input. It takes the hidden state, and it takes our input vector. Okay, the input vector basically represents our word. Okay, again, the recurrent cell basically takes two inputs. First is the hidden state, and then there is the input vector, that is our word. And then what happens is, for each input vector, for each word that we send to this recurrent cell, what happens is the recurrent cell produces one output. Okay, the recurrent cell produces some output. So basically, let's say you send in one word to a recurrent cell. What it will do is it will produce one output. Now what will happen is it will basically calculate the hidden state. Okay, it will calculate the hidden state, and then it will through the loop it will pass that same hidden state to itself. And then when we pass the second word, okay, that is a second input to the same recurrent cell, then again the recurrent cell will take the same hidden state as the input and another input word as its input. Okay, then it will produce an output, a certain output. Okay, now what will happen is here, now again the hidden state will get updated, and the hidden state will again be passed to the next loop. Okay, so now when we give input our third word to the recurrent cell, the same hidden state will again through the looping mechanism will be input to the recurrent cell, and will get another certain output. Okay, so what we are doing is we are through this loop we are basically passing the hidden state again and again to the recurrent cell. Okay, so at each point the recurrent cell basically gets two inputs. First is our input vector, that is our word, and the next is the hidden state. Okay, the hidden state vector. Okay, every recurrent cell basically takes two inputs at any given time. The first input is the hidden state, and the other one is actual input, that is our word. So the hidden state, the hidden vector basically gets updated again and again. Okay, it gets updated again and again as we give multiple inputs. Okay, as we give multiple inputs, so the hidden state basically by constantly getting updated, it basically stores the information, it stores the relationship among the various inputs, and it then helps us gets our required output. Okay, so one example would be this. So you can see that at the beginning the hidden state is just 0. Okay, hidden state has all the values as 0, and then when we, let's say I want to input the sentence I am Groot. Okay, when we give our first word, that is I as vector, the recurrent cell will basically take two inputs. First is the hidden state, then it will take the input word. Okay, and then it will produce a certain output, it will produce certain vector. Then what will happen is our hidden state will again get updated, and we will pass the hidden state again to the recurrent neural network, and then we will pass our next word to the recurrent cell. Now again we'll get a certain output, and the same thing will happen again. The hidden state will get updated, and the hidden state will again be sent to the recurrent cell along with our next word, that is Groot. Okay, then again we'll get a get a certain output. Okay, so basically what is happening is we are trying to update our hidden state to maintain this relationship among multiple inputs. Okay, it's not that complicated, it's very easy. And one very important thing is that depending upon the task at hand, we can either ignore the outputs at each step, or we can keep track of them. Okay, so the outputs that we get at each point, we can either ignore them all, or we can only consider one of them. Okay, depending upon our task. So for example, if we are doing, let's say, language translation, then in language translation it is a many to many relationship. So we'll basically will will not ignore all the output vectors. Okay, because we want to basically calculate, we want to translate one sentence into another sentence. Okay, so we will not ignore the vectors. But let's say we are doing sentiment analysis. Okay, then in that case we may ignore this to all the other outputs, and we may care only about the last output. Okay, last output, because in the sentiment analysis what happens is we want a sentiment, we want to predict the sentiment. Okay, so once we have passed the entire sentence, we will basically ignore all the outputs except the last output, which will be our prediction. Okay, so depending upon the task at hand, we can either we can either ignore all the outputs or we can keep them. Okay, so this is very important. Let me clear this. Okay, so now let's look at how one recurrent cell actually works. Okay, let's look at how one recurrent cell actually works. So the working of a recurrent cell is also very easy. Okay, a recurrent cell basically at any point takes two inputs. First is the hidden state, and then there is the word, okay, which is in a vector format. Okay, and we basically have three weight matrices. So you may see here we have three weight matrices here. These weight matrices are the learning parameters here. So the main goal of our recurrent neural network is to find the most optimal values for these weight vectors. Okay, so we have three weight vectors, w1, w2 and w3. Okay, so what happens is, now when we at any point when we give our hidden state and word vector to a recurrent cell, what happens is, the first step that it does is it multiplies the input vectors with the weight vectors. So for example, here let's say we have some word. Okay, it has let's say we have some word which has converted into a vector, and we pass this word as input. Then what will happen is, at first step it will this vector will get multiplied with the weight vector. Okay, so and then their product will be basically added with the multiplication of the hidden state and the and another weight vector. So our input gets multiplied by input basically gets multiplied by w1, and our hidden state gets multiplied by w2, and the result of these two multiplications is then added together. Okay, it's added together, and when it's added together we get one single vector at this point. Okay, now this vector is then passed to an activation function. Okay, this vector is passed to an activation function. All right, so now what happens is, this is basically the hidden this new vector, after passing through the activation function, becomes our new hidden state. Okay, becomes our new hidden state. Okay, now there are two things that happens to this hidden state. Firstly, we use this hidden state to calculate our output, and secondly we use this hidden state to then secondly we pass this hidden state again to the same recurrent cell as the input. Okay, so what happens is, we have our hidden state here, updated hidden state here. We multiply this hidden state with w3. Okay, and we get a certain output. Okay, we get a certain output, and then we pass this same hidden state again to the same recurrent cell, along with the next word. Okay, so again then the same thing happens. The input vector is multiplied with w1. The previous state is the hidden state is again multiplied by w2. Then the result of both multiplications is added and sent to through a activation function, where we get another vector, and this vector is then basically our new updated hidden state. Then this updated hidden state is again used to create the output of this recurrent cell, and again it is passed as input to the next word. Okay, so this is what happens inside a recurrent cell. Okay, so you can see here we are passing our hidden state at each point. Okay, we are passing our hidden state at each point, and the hidden state basically what it does is it just helps the recurrent neural network maintain the relationship. Or all right, so yeah, this is how a recurrent neural network works. Okay, just remember that depending upon the problem, we will either ignore the outputs, or we'll not ignore the outputs. All right. Okay, so now there are different types of recurrent neural networks. Okay, now even though the main reason for recurrent neural networks, the main reason recurrent neural networks were built was for maintaining sequential data. for maintaining sequential data, the recurrent neural networks are still not that great at handling sequential data. Therefore, they suffer from a problem called as short-term memory. Okay, short-term memory. Now, if you have a sentence for, if you have this sentence that deep learning is upcoming field in today's technology, but it is very hard. If you have this sentence, now the model, it becomes very difficult for the model to find the relationship between the first word and let's say the second last word. Okay, so the model basically kind of forgets. Okay, in short, RNN forgets information, so it's still not pretty good at handling long-term dependencies. So that's why, in order to counter this problem, we created many other extensions of RNN. Okay, so some of those extensions are LSTM, GRU, and bidirectional. So now, whenever we talk about recurrent neural networks, we will basically most commonly be talking about LSTM, which is basically the first extension of a recurrent neural network. Okay, so keep this in mind. That depend So in order to counter the short-term memory problem, we created multiple extensions of RNN, okay, which are very good at handling long-term dependencies. So yeah, this was it about recurrent neural networks. In the next lecture, what we'll do is we'll try to implement sentiment analysis using LSTM using Keras. Now remember, the main difference is only in the architecture. Okay, all the other things happen in the same manner. Okay, the only difference between RNN and LSTM or any other extension is in their architecture. They are just a few small changes made to the architecture. The rest all the other concepts remain the same. So yeah,